Hi there from London. I'm super bummed to be talking to you from a screen today instead of being there in person. Nextflow is one of my favorite bits of scientific software, and the community you've all built around it is, well, it's inspiring. I get my batteries charged every year by coming to Barcelona to see the incredible stuff that you're all doing. And so for me, this is the conference that I actually look forward to. All of the other ones at work. Unfortunately, my doctors have put me on a no-fly list while they fix a thing in one of my eyes that is apparently pretty sensitive to air pressure right now. So my friend David Lecomber from ARM is going to pick up the baton from me to tell you about the work that we've been doing across the community to help bioinformatics squeeze more cycles for less money and even less carbon using ARM processors like the AWS Graviton. Now, before we get to that though, I want to do a very short recap of some of the things our teams here in HPC Engineering have pushed out this year, which are pretty meaningful for the workloads that you're all driving. There's a handful of AWS services that you all appear to be using heavily, and there's a new one that I want to mention because it'll be interesting to at least some of you. The big one, of course, is AWS Batch. Batch is our always-on container-based scheduler. Ever since I sprung for lots of pizza and Red Bull at the hackathon we did here in Barcelona in maybe 2017, I think, Nextflow has had a great integration with Batch. Now, since Batch is pretty awesome at scraping EC2 spot pools for all the leftover capacity here in AWS, you've all been hammering away at this service and solving lots of thorny problems and doing it on the cheap, which is something I completely endorse because science. Now, Batch grew a few new capabilities this year. A big one is multi-container support. Before this, every batch job definition could only refer to a single container, so that if you had anything complicated to do, you had to change the way you built your containers, which isn't the right way of doing it. Now, lots of folks asked us for sidecar container support, and even more were just asking us to decouple the container definitions from job definitions. So we did that and launched this new thing back in April. The robotics community were pretty happy about it, and I'm pretty sure there are some Seqera CTOs in the audience who may even be quietly smiling as well. So we've released a very cool thing a few months ago that we bagged under the heading of blocked job queue detection. You've probably all had the experience at some point of having one of your batch job queues get plugged up by some job at the head of the queue that's stuck in runnable but isn't actually running, and it holds everything up behind it. Anyhow, this new feature scans your queues and tries to detect these things, and it goes a step further because it can also send CloudWatch events to you or to EventBridge so you can take action programmatically if you want to. Now, for those of you working in environments where you're using Batch and sharing it amongst different groups, running different workloads with competing priorities and often shared budgets, please don't overlook the big feature that we released last year in 2023 called Fair Share Scheduling. There's still lots of people laboring with FIFO queues who haven't heard about this yet. Angel Pizarro from my team, who is our bioinformatics nerd and batch geek, wrote a very useful blog post explaining how it works. I'm going to link it here. You should totally read this thing. Now, I mentioned a new service. It's called the AWS Parallel Computing Service. We launched it just a few months ago. PCS for short. You can think of it as a Slurm-based equivalent of Batch. It's always on, it's waiting to receive jobs, it spins up compute fleets to run jobs when they arrive. But it's more like a traditional HPC environment that you're probably running on site, which means you can use the job scripts you have, and you get a lot more say and control in how the jobs are spun up, and you can even log in to login nodes and things. But if you're happily using Batch already, I'm not going to suggest you change a thing. This just gives you another quite interesting option, especially if you're trying to think about workload types at your place that aren't as container friendly as your bioinformatics workloads. Now, in the last few years, you probably had to have been hiding in a cave somewhere to have missed the news that ARM-based processors are storming into data centers everywhere. This is what David is going to talk about next, the work that he and the team have been doing using our implementation of an ARM processor, the AWS Graviton. Every year or so we announce new silicon, and this year we launched a new series of EC2 instances based on the Graviton 4 chip, which is our latest. These things are very punchy processors. Graviton 4 is the first generational step where we've seen everything just go faster, no exceptions. Now, we can bang on about the architectural beauty of these little suckers, and we might just do that if you're standing too close to us and we have a drink in our hands, but the best things about these little beasties is that they're cheap, they're fast, they can do anything an x86 socket can do, and they're really, really power efficient, which means low carbon. Now, if that last thing, carbon, means anything to you, and it should, it may warm the cockles of your heart to know that we, Amazon, just landed on our target to be 100% renewable energy powered this year, a few years early. That means that if you run a workload on EC2, your carbon footprint just became teeny tiny. The task at hand, though, is to get all of the open source codes in the world running on these CPUs, so it's just easy to leverage them. Now, from the experience we've had in the wider HPC community with the SPAC project, we noticed that most things actually just compile. And the most you ever need to do is typically fight about fixing some CMake scripts, so they refer to the right math libraries or GCC command line syntax. We already know that about 80% of what's in Bioconda will run happily on ARM processors. Phil, Pablo, and some others are working to pull together some telemetry so that we can know what's going on in that other 20%. A small percentage of the time, and it is pretty small, we find out that some super nerd writing a downstream I/O library decided to hand code something in assembler, mainly because they just wanted something to go extremely fast and they knew how to pull it off for that processor. Porting that stuff takes work. Some percentage of the time, we're going to see these packages that just compile and run fine, but they don't run fast. And amongst all of the Bioconda packages we've seen so far, these pathologies are actually pretty rare. When this happens, though, we have nerds like David and his team and my teams here in AWS who know how to deal with this stuff. The challenge we have, though, is knowing where to send those folks, and this is where we could do with your help. If you're up for investing a small portion of your time to pull ARM-64 containers instead of x86 ones from, say, Seqera Containers, and take one or two of your pipelines for a walk, you'd be contributing a lot to this effort and helping us close that gap really quickly. I'll go one step further and say that if you're up for doing this, I'll get you some credits for some free Graviton, so it's not costing you anything more than your time. Just get in contact with me. So here's what we need you to do. Try it. And if it doesn't work, tell us. That's basically it in a nutshell. We're going to make that last part easy. On the NF Core and Nextflow Slacks, you'll find a new public channel called ARM-64, where you can drop in and report anything that isn't working. There's also GitHub issues, of course, for this, but the ARM-64 Slack channel will probably be more interactive, and it gives us a chance to get some insights into who's having problems with what, and potentially spot some trends. We may also be able to help yourself by suggesting some easy things to try, so you can get going even faster. By the way, you should also feel welcome to report stuff that is working, because it's nice to get good news every now and again as well. Historically, the transition between big CPU generations in scientific computing has usually taken many, many years, and some things never made it. The transition to ARM-based lifeforms has actually been surprisingly quick, but I'm impatient for the progress we all want to make, so I just want this phase over really soon. Now, that gets me to the final thing that I want to say before I hand over to David, who's there in person. I will never get tired of pointing this out to you all. You, the assembled scientific nerds in the audience there, are the rarest species of animal ever to walk the earth or inhabit this corner of the universe. It took at least 2 to 3 decades to grow each of you from little science nerds into the people that you are working at the bleeding edge of scientific discovery today. If we're to make the kind of discoveries we all need to live longer, healthier lives in our lifetimes, we can't rely on growing new scientists out of schools, because that won't bear fruit soon enough. We need to make each and every one of you the most profoundly productive people you can possibly be. My role in that is to figure out how to equip you with practically unbounded compute tools so you can just calculate, simulate, and noodle over new ideas whenever they happen. The sooner you experiment with a new idea, the sooner you can figure out what the next idea is that comes from that idea. And the sooner we'll be able to get cures to horrible diseases or discover insights that let us all just live longer, happier, and healthier lives. David and I, and a lot of others, are working on making that cheap, fast, and very, very available, so anyone with a problem to solve can just solve it. Don't be shy. Let us know what you need to pull that off. There's literally nothing higher on my priority list than making you all more potent at what you do. So thank you, by the way, for everything you do. You're an amazing group of people. Have a great week in Barcelona. I really, really wish I was there, but I'll see you in 2025.
Great. Morning, everybody, and thanks to Boof. I'm sure he's on the web listening in on us today. Really thrilled to be here. It's my first Nextflow Summit. I have the badges to prove it, and I'm a fully fledged Nextflow noob now. Been having a great few days here, but it was a hackathon yesterday, and the day before, which have been really good. So I want to talk a little bit more about what Boof's been talking about there. And what we'd love to do and achieve with this community. I spend my days working with people in the scientific communities across so many different fields. And genomics is just amazing. I absolutely love that this is a field where every one of the people I'm working with is having an impact on people every day. And it's just amazing. You can't say that about everything that people do. But what you do is so important, and I just want to put a lot of effort into this, making it successful. So let me talk about what Boof was saying about this ARM technology that AWS is deploying, about faster, cheaper, greener processors. And I'll do that by talking a little bit about who ARM is, and what's going on, and how we would love to work with this community. So ARM's different from a lot of companies in the semiconductor industry. We develop IP and we license that technology so that other people can take our building blocks and build things for what they want to achieve. And this model has been behind the 30 years of growth our company's had. In smallest devices, you find ARM technology in things like washing machine, your hairdryer, everything these days. Right through mobile phones, and these days, where almost all mobile phones, the designs are on ARM now, ARM architecture, and right through now to servers, networking, edge devices, and supercomputers. So people take those designs and do things for their environment, what they need. And as we heard, over in the cloud, a lot of servers are deployed. It makes a lot of sense to design chips that are able to be environmentally power efficient, have performance, and really suited for the workloads that the clouds are trying to deploy. And at the scale that they want to deploy these things, investing in their own development makes so much sense. So AWS are on their 4th generation now of what they call the Gravitons. The Graviton 4s only came out a few months ago in general access. But Microsoft Azure, they now have what's called the Cobalt 100. That went generally available, so anyone can log on and get one just about 2 or 3 weeks ago. Oracle, they're using, in Oracle Cloud Infrastructure, there's the Ampere ones, which they're a company they work with a lot. And then Google Cloud, actually it's just yesterday, the Google Axion, which is their ARM-based server, went live for everybody to be able to access that. So what we're talking about today, and what we'd like to do with the Nextflow community, is not just going to apply to running on AWS. It's not like you do all this work and you can only run in one place. Nope, all the clouds are doing this. It's really everywhere, and there's an opportunity, whatever cloud you're working with, to take advantage of what our partners have been doing. And if you're not working in the cloud, that's okay too, because there's also what you do for supporting the ARM architecture can also be working for you on-prem as well. So NVIDIA is one example of one of our partners who's designing a CPU. It's called NVIDIA Grace. It's actually out there now, which is, they've taken our cores and they've put all that together with a load of things that design choices that they made to make this the most power-efficient server chip available on-prem. For example, one great example, in addition to our sort of power-efficient cores, they've also plugged into the unit there low-power memory. And when you add all these things together they've done, it's roughly twice the performance per watt of any other server of that generation. So, it's fantastic stuff that's going on. And we're seeing those now starting to deploy in some of the largest supercomputers on the planet. Over in the UK, Bristol's got 2 systems. So they've got one which is NVIDIA's CPU only, and another which is the UK's largest now, which is NVIDIA's CPU, it's NVIDIA GPU. So obviously, NVIDIA, obviously very well known for their GPU, but by designing an ARM chip that could go alongside that GPU, they can achieve far more benefits for their GPU business as well. They're able to get data transferring over faster and that kind of thing. But the CPU only side of it, it's a standalone. You don't need the GPU, and you can just run regular ARM CPU workloads on that. So in Bristol, they've got a GPU system as well as a CPU only system. Over in Switzerland, the largest supercomputer in Switzerland is now an NVIDIA Grace Hopper system. In Germany, in Jülich, they're building the EU's largest supercomputer, which is going to be NVIDIA Grace CPUs plus NVIDIA Blackwells, the GPUs. And then there's other systems such as Los Alamos. And closer to home, there's some Grace CPU superchips going in now in Barcelona as well, in the supercomputing center there. So somewhere you're going to have access to these things on-prem, if not already in your laptop. Yeah. And we do, the success of using an architecture is really not just the not just the processors, it's the software ecosystem. And this is a long-term thing, long-time thing. It's not easy to switch from one architecture to another. There's so much infrastructure on which the world is built. And so ARM has been doing this for over 15 years. There's hundreds of software vendors involved that support ARM now. Hundreds of open source projects, actually probably thousands, if not tens of thousands or millions, who knows? But there's so many now that run on ARM. Things that you rely on like Docker, that's there. And so there's lots of companies worldwide working on ARM. And the reason all of these things work is this ecosystem, this software ecosystem. It's kind of, ARM was involved in priming it at the very start, and we continue to invest an awful lot in software. We really do. It's so many software developers inside our company. But also all of our partners, folks like AWS, folks like NVIDIA, Google, and others, they want ARM to succeed because they're building CPUs around it. And so we want them to succeed too. So we've all got this mutual shared interest in making this successful. So ecosystems, we're all about those ecosystems. And so it's working really, really well in so many communities, and so much of that, all that fundamental stuff is there. And the community I want to see really enabled and running at full speed is obviously genomics, because this is hugely important. Everything, as I said, that this community does, it's important. Is it feeding us? Is it helping us to lead longer, healthier lives? About 6 months ago, I was working with GenCove and Sentient, and they were doing a lot of work on animal genomics as well as human genomics, and we did a case study on this, and the net result of this was they've already been running on Gravitons for some time, the Graviton Freeze, but when we actually looked at all the costs of things and what they were doing, we basically benchmarked against every other platform we could have found in AWS. And it was about 1/3 cheaper than any sort of Intel or AMD-based instance to run on an ARM instance. So you think about 1/3 cheaper, that's actually 50% more results for the same budget. So that's hugely important. You go home and think, I could do an awful lot more without spending any more. And the one thing you need to make that possible is the ARM architecture. Or the ARM architecture to be supported within what you're running. So where are we today? What would we like to do with Nextflow Core and with also the infrastructure on which it's built, like Bioconda recipes, Conda, and so forth? It's actually only just the start of 2024, spring 2024, when Bioconda utils became available and fully supporting ARM. It was, they've got the CI infrastructure in place. A lot of hard work, lifting and shifting to make it be able to do multiple architectures. Big thanks to if you were involved in any of that effort. But with that in place, that meant other things suddenly became possible. Recipes were getting contributed in all the time. Nextflow, NF Core, they'd already been working, folks here in Seqera have been working on the ARM support since way before the Bioconda utils became available, but this just was kind of like a bit more steroids in the system. So yeah, Bioconda recipes, there's around about 80% of them today supporting ARM just out of the box. You do a Conda install and it's there. So it's moving quick, but there's still 20% to go, and that's where I'd love to see more community effort. Over the last few days in the hackathon, we've had some, working with Rika and Pablo and others from Seqera. We've managed to contribute a few recipes in there, and because the problem is a pipeline. You've got lots and lots of recipes within that to make that pipeline, and if 20% of them of all the recipes are missing, maybe your pipeline is going to rely on one of them. 90% of the pipeline might be fine, but then there's like one or two that don't work. So you kind of need to get as many of these as possible. But when we start looking at it from a pipeline perspective, there's about 1/3 of all pipelines just work out of the box already. You just, flick that switch in the Seqera website, for example, when deploying, as Boof was showing well on the screenshot. Click that, and you can run on ARM and start benefiting already. For some of the others, they don't work. But the important ones, that's what we're going to try and fix. That's what we want to work with the community on. But some of the really important ones, like RNA-seq, that's already there. And I'm going to talk about that in a second. I think SAREC, over the course of the next 10 days, that'll start to work. So really important pipelines. They've got a lot of things inside them, but those really important ones we want to focus on. We want to make sure they work. But we rely on the community telling us what's important as Boof was saying there, we don't really know in ARM or AWS what it is that matters to you. We're not going to be running this day in, day out and saying, how fast should that be? Is it you know, is this right? Is this somewhere where we should put some effort? Or is this really 10 seconds in a workload that lasts a day? You know, this point us in the right direction. We want to help. We want to work with that community, with the community. So if we take a look at RNA-seq, just say it's not just, you know, my examples say there on the previous slide where we were working on one particular, the numbers for Genco and Sentient, where it was one particular application in it. Now, when we look at a full pipeline like RNA-seq, on this chart here, we've got the total runtime in the left thing there, and the dark-colored time at the bottom there is one of the ARM instances, and there's 3 different Intel instances above that. As you can see, total runtime for the entire pipeline, very comparable, in fact, very competitive versus some of the others there. The cost, on the other hand, for getting that performance was, you know, as you can see, substantially less. So thanks to the folks in Seqera, particularly Pablo and Phil, for running these and for their work in making this possible. We actually ran these on Graviton 4s. We were using what we call the R8G instances. So there's in the last few weeks, there's been more of these, more instances behind the Graviton 4 brought out, M8Gs, C8Gs, and so on. They're not in every availability zone yet, but obviously that's going to come over time. So this particular cost here would probably be less if we were using something more typical of the workflows, like a C instance, or perhaps even an M instance. Turns out memory is actually quite an expensive part of running a system. But even when we've got a pipeline working, you know, we still need to know when, as I say, whether something's, you know, slow and should be running better, because sometimes there's things that's been really highly optimized. As you've said, you know, somebody's put some assembler in there or something like that. Or something's just not right. There's a library that's used, is not got the right compiler flag or anything like that. And we're not going to know. Fortunately, the folks at Seqera put together some nice tools. We're able to see the difference in runtimes between various parts of the workflow. So what we're seeing here with this chart here, where a dot is below the line, this is where Intel is slower, and where a dot is above the line, that's when ARM is slower. Okay? So we can see broadly comparable, but you know, there's no reason why an ARM core should be slower than an Intel core on these things. When you think of similar generations with the same speed processor and the same speed memory, that kind of thing, these things should be pretty close. You know, wild differences are something we really need to look at. And so one example of that, actually, the other day, Phil and Pablo brought to us was Salmon, because they were seeing it actually running slower than they expected on versus AMD Genoa when they were running on Gravitons. And when you coupled in multiplying out the cheaper price of the Gravitons, it was still, you know, it wasn't the knockout blow that the running on Graviton wasn't the knockout performance blow we wanted to show and cost blow. So it turned out, of course, at that point in time, that was run on the Graviton 3 because the Graviton 4s were only just becoming available. And so that's the middle. If you look at this graph here, we've got two charts. The one on the left is what Salmon was like when we first looked at it. The middle bar is the Graviton 3. It's been out for going on 2 years now. On the left is Genoa. It's also, you know, way over 12 months old now, but fastest AMD thing inside AWS. But so first thing we did, obviously, just run it on the latest thing, get hold of a Graviton 4, see if the numbers change, and they did. Now we had performance parity with Genoa, but we thought, let's have another look, let's see if we can do even better here. And we put on a bit of profiling into the application itself, had a look at some of the things that were going on, found a library that was widely used library, as it turned out, not just in genomics, that was doing something really slow when it came to some maths, which was only being done when it was on ARM. So we contributed that as a GitHub request, as a GitHub issue to the package, but also made the changes into Salmon and a couple of other changes in Salmon and some of its dependencies like pufferfish. And net result, we got something where Graviton 3's performance came down nicely. Graviton 4 is now much faster there than Genoa. But that's just time. what about money? I did promise something about saving money somewhere earlier today. Well, this is what it would look like if you're running on demand. There's a difference in price between Graviton 3 and Graviton 4. You are going to pay a little bit more for the cores on Graviton 4 than you are on Graviton 3. But on the other hand, the performance is better on a Graviton 4. How does it look in practice? You can see Graviton 3, Graviton 4 very close on the cost front, but they're definitely better than running there on the other architectures, such as the AMD architecture there. These particular numbers, because of the size of the test case, we couldn't run, we had to run an R series, which has got more memory. When we were on 4 cores, it needed about 30 gig. And when we were on 8 cores, it was okay to go into M series. So that's how things vary. That's probably why some of those costs are most varied there. But just for clarity, that's what was used there. But that's the on-demand. One thing about genomics is it's a real good place to use Spot. I hope as many of you as possible are using Spot. But I took some numbers last Wednesday overnight, had a look at what was going on in Frankfurt, where you can get the Graviton 4 instances. As I say, they're rolling out to more regions all the time. The dark blue bars here, so I know there's a bit of an eye chart, but the dark blue chart here, this is the sort of on-demand cost, and the light blue is Spot. As you can see, across all platforms, it's like, massively cheaper to run on Spot. But with Spot, you do risk that termination. So you've got Genoa on the left and Graviton 3, then Graviton 4. But yeah, with Spot, there is that termination risk as well. But if you don't think about that termination rate, then already the Graviton 4 was 30% cheaper than running on the AMD Genoa. But when you looked at the termination rate as well with the Spot, we were only having a 5% termination rate for running on Graviton 4, so you weren't having to rerun. There's much less chance of needing to rerun a workload as well. So lots of good reasons to do that. You're not recomputing, you're saving money, but also, as we said earlier, it's a much greener platform as well. So to the community, really, really, we need your help. We don't know what's important. We want to help. We'll be the nerds that will do some of the more complicated things in there, but we want the community to tell us what needs to be done to just contribute in any which way you can. Try your pipeline. Raise issues on GitHub. Reach out on that Slack channel. Take a look at the performance differences between the two. Tell us where it's wrong. Tell us where to focus our time, and we'll do that. And finally, this is the Slack channel. Look forward to contributing, working with you all on this. But yeah, I'm around until just after lunchtime. So if anyone wants to see me, just do grab me during one of the breaks. But we've had a good few days here, made some good contributions already into Bioconda recipes, making progress now on some of those pipelines. We should get the numbers up really nicely quickly, but we'll get there even quicker with your help. So thank you, everybody.
Thank you, David. First question, does a scientist who's concerned about the reproducibility of their analyses need to worry that a change in container architecture might result in slightly different data coming out?
I think that's going to depend on the applications themselves. I don't know the answer to that. It's more of maybe perhaps there's a regulatory channel thing for validating it. But ultimately, when you try a new version of any of these packages on, going from version 1 to version 2 of anything, do you see a difference in changes? It's probably that kind of thing. I spend a lot of my time working with folks in scientific computing, and some of those communities, they want to be to the last decimal place in very long numbers accurate. Weather community in particular always want to compute the same number they got the last time, even though it's quite a lot of randomization in what they do. So I don't know. What we're saying is the quality tests and things that are coming out of these workloads, they should be testing for this, and when it's not matching, there's a problem. But it should, because you can get the same random number sequence generators. Any areas where there's randomization in there should be exactly the same. In fact, the genomics world, so much of what's done is not in 64-bit floating point. I'd be surprised to see differences, put it that way. And another thing to also point out is because ARM is an architecture, and we've had all those other partners who are building chips, not just AWS, when you've done that work that's running, because it's one architecture, when you've done something that is working on AWS, you can take it to any of those other platforms, and you will get the same result because it's the same architecture.
One more question. Sort of at a high level, what are the types of improvements that the nerds at ARM need to make to a process like Salmon to make it eke out that extra 8% of performance?
Oh, you know, this is great. It's one of the fun parts of my job is finding things and surprises. And that's what you see, it's just surprises. So for example, sometimes we discover things in the compilers that are just not optimized, you know, and we've got a great compiler team doing GCC and LLVM work in ARM, as well as math library folks and libc things. And I'll say, you know, we found this. And they love these kinds of things, given a real problem, and they'll solve them. But when it comes to actual packages, I guess I could say, looking at Salmon the other day, it used libboost. And for some reason, it was trying to do 128-bit floating points, which are not hardware supported by anything. And it was just going slow. And it's quite bizarre, because it's such a well-used library. It's not just in genomics. And it was just a case of a hash define saying, don't do that. And the problem went away. We had another thing. I think that you get things like, say, BWA-MEM2, which we've been working on this week. That had some hand-cranked assembler putting probably about 10 years ago. And there are tools that actually let us migrate that over to ARM, ARM's equivalent of that assembler, in a sense, just by including header files. And that's what we did. Otherwise, it would have gone through the native code that didn't have all the benefits of that, and it would have been a bit slower.
Okay. Well, thank you so much.
Thank you.
This is one more hand for David Lecomber and Brendan.